Okay, you can see the results. Let me share the screen. For the first question, I hope you see why the von Neumann entropy is 0, because you have a pure state. You don't need to do any calculation. You have a pure state, which means that your total entropy will be 0, right? Because we have seen that you can previously we have seen that if you have even a state like this, 1 over square root 2. So even if you have, let's say, 1 over square root 2, 0 plus 1, then I can write this state as some plus state, right? And then my density matrix would be simply plus plus, right? And we saw that for such a pure state, although it's a superposition, still the entropy would come out to be 0, right? We have seen that in yesterday's lecture. Whereas if you have a mixed state, then you do not know the outcome. If you have a pure state, it is saying that you know specifically what you're getting. But if you have a mixed state, you do not know what you're getting. So the answer for that would be 1, whereas for a pure state, the entropy is 0. So we'll try to do that again. And then let's see for the third question, where we're talking about the Bell states. Some of you answered A. First of all, that is not even normalized. So it doesn't even have total probability of 1. So it's not even a valid state, right? And then C is not an entangled state, right? You can see that it can be expressed as a separate product. And D is not a state. So it is a density matrix, actually, right? What I'm representing there. So the answer should be B. So a bunch of you have not answered correctly. So even by elimination, you can see that B should be the right answer if you didn't know what the Bell state is, because A, C, D are not even valid states. For the A and D are not valid, and C is a separable state. I hope that makes sense. Any questions? Okay, so then let's go back and see what we did yesterday. So maybe because some of you did not answer the questions correctly, let's quickly recall what we did. We defined von Neumann entropy if we have a bipartite system. That is, we have some state that is shared by two, Alice and Bob. We defined the joint entropy the way it is here, right? That is, you take the joint probability and take the log of that. And it's a trace of the density matrix. And if you want to talk about just Alice or Bob, then you can take trace over the other person. That is, again, going back to our joint probability distributions. If I want P of X, I take sum over Y, P of XY. So similarly, if I want rho A in the density matrix, then I take trace over B, rho of AB, right? And then we defined two other things: conditional entropy and mutual information, right? Conditional entropy is basically we defined as S of rho AB, right? And in case of quantum, we saw that S rho AB, the conditional entropy, can be negative. In fact, we saw that this is -1 for a maximally entangled state. And then mutual information is defined as S of rho A plus S of rho B, right? Minus whatever is common, S of rho AB, right? So this was again inspired from like if you think about two sets A and B, right? Then A union B would be equal to A plus B minus A intersection B, something like that, right? So you can think of this as A union B and the mutual information as A intersection B. That is, the both parties know it, right? So this would be something like A intersection B. Are you able to follow that? Any questions? So the biggest challenge in quantum information is that in classical, we can read it without disturbing the state, but here we have to make a measurement, and we when we make a measurement, we disturb the system. So let's look at the example here. For example, a Bell state. If we have psi minus, which is entangled, right? So you can see that this is a state where you get the joint entropy for a pure state to be 0, right? That is, if you take the total state, that is. But if you take a reduced state either over A or B, then you do not know which one is 0 and which one is 1. So you have a maximally mixed state, or you get the entropy to be equal to 1. And we saw that the conditional entropy for that should be -1, right? And the mutual information is 2. That is, you have 2 bits of correlation between qubit 0 and qubit 1, right? So each subsystem may be maximally uncertain. That is, if I look at just Alice's bit or Bob's bit, then that may have a non-zero entropy, but the joint state is pure, meaning that all the information is encoded in their correlations, right? Now let's do another simple example so the concept of information content becomes clearer. And this is the quiz question. So let's say we have a state plus, right, which is defined by 0 plus 1 by square root 2. What we would like to find is the entropy if the measurement outcome is known. So if the measurement outcome is known, then what would be the entropy? Anyone? Entropy is uncertainty, right? And you know the outcome, right? It should be 0, right? Because you know the outcome. And so the measurement outcome, if it is known, then the entropy must be 0. Because, it is either 0 or 1, and whatever that may be, you know it. That's what the question is saying. The measurement outcome is known. Then the second part is, what would be the case if you have the measurement outcome that is not revealed? For example, say due to decoherence or due to some noise or whatever, right? So you can see that if the outcome is known, then it's a pure state, and we can show that the outcome is known, so the probability is 1, so the log of 1 gives you 0, so then you get 0 outcome, 0 entropy. But if the outcome is not known, then our final density matrix would not be a superposition state. It would actually be a mixed state. That is, we do not know the outcome, right? So then we write the final density matrix as 0, 0, and 1. So note that this density matrix is not the same as this part, right? It is not multiplying. So this kind plus plus is not equal to 1 over 2, 0, 0, plus 1 over 2, 1, 1. What this means is this is for row 0, this is for row 1. So here we are directly adding the probabilities. We are making a convex combination, right? So that is not equal to plus plus. This is a pure state, right? This is a pure state. Here our outcome is not known. That is, I have already made a measurement. The probability is half for 0 and half for 1. So I have a maximally mixed state. Therefore, I have maximum entropy, right? So I have 1. So the pure state becomes a mixed state due to lack of information because the outcome is not known. So the entropy increases from 0 to 1 bit. I hope that makes sense, right? So if you make a measurement and then you know the state, the outcome becomes certain, then again the entropy reduces, right? So I hope you're able to follow through with how the entropy is changing. Any questions on that? Okay. So okay, there's some question. Okay, no questions. So similar to Shannon's noiseless encoding theorem, we can talk about, so in case of Shannon's theorem, we said that we need at least h of x bits, where h of x was defined as minus j pj ln pj, where pj is the probability that Alice sends a message xj, right? So whatever is this, the maximum pj, for that we calculate the entropy, and we need at least those many bits to exchange the information. And basically, we're putting the same thing in terms of the quantum, but except instead of h of x, we define von Neumann entropy. So you need at least the von Neumann entropy determines at least those many bits you need. So that sort of summarizes what we discussed yesterday. So we can get into more discussion into what we mean by a quantum channel and talk about how we can represent quantum channels. So we talked about Alice and Bob, right? Again, this need not be Alice and Bob. This could be, your initial state and your final state, and we have some quantum channel in between, right? So, and then that quantum channel here could be whatever, some gates or measurements, whatever you are applying here, right? So whenever we talk about Alice and Bob, they don't need to be people. You can consider that as some initial and final state, and the quantum channel as some gates or some operations that you're performing in between the initial and final states. So this word channel we're deriving from communication theory, but it doesn't mean that there is actually communication. It could, any process can be considered a quantum channel, right? So again, we have state some rho, and then it goes through the channel and becomes phi of rho, where this phi represents whatever noisy or imperfect processes that would modify the initial density matrix. And what is the output that comes through the channel? That must be another density matrix. So whatever this quantum channel does, it must give you another density matrix again, right? The density matrix meaning that it should be trace preserving, meaning that recall that whenever we have a density matrix, the trace of no matter what the density matrix is, by definition, we must have the trace equal to 1 because the total probability must be 1, right? So whatever is the quantum channel, it must preserve trace. So that's why sometimes it's called trace preserving and completely positive because our probabilities range between 0 and 1. You cannot have a negative probability. So whatever is the output, phi of rho must also be a density matrix, right? So it may change the elements, but the overall output must also be a density matrix. So sometimes it's called a super operator, or TPCP or CPTP, whichever way you want to call it. But that means it is trace preserving and completely positive. And the reason we are developing this, whatever we are trying to do, is to model the decoherence or the noise in the system. So there is some question. So a channel is not a physical entity. It is a physical entity, right? You're passing it through some gates or some measuring device or whatever that is, right? So let's say if I initialize some qubit in some 000 state, right? And then I perform some operations, like I perform some Hadamard gate, some X gate, Hadamard gate on 0th qubit, X gate on 3rd qubit, and then let's say some other gate R1 on 4th qubit, whatever that may be, some operations. And then I get some output, whichever is some final state, right? So these physical operations or whatever is happening in between is, you can consider that as a quantum channel, right? I mean, it is still a physical medium in the sense that, you're passing through these different gates in the sense that you are physically manipulating, but it could be physical channel, meaning, for example, if you are actually communicating from one node to another node, let's say through some optic fiber, right? Then it could be, if that's what you mean, is it like a fiber optic cable or something? It could be that fiber optic cable, right? But what I'm trying to say is that channel is not limited to just whatever theory we are going to develop about channels. It is not just limited to communication between Alice and Bob and a fiber optic cable or something like that. But you can consider that in any operation, like these gates or any measurement. If the state has been prepared with some noise, that also we are considering in phi. So if so we do not know whether the state is prepared with some noise or not. So that's the tricky part here. So we assume that we're preparing state without any noise. And to model the noise, we are trying to build this theory about quantum channels, so I can make some operator that would give me from what would be, no noise state to a state with noise, right? So that's the goal. Any other questions? So this channel could just be like, for example, if I prepare some state, let's say I prepare some state 1 qubit state 0, right? I prepared at t is equal to 0, and I'm not doing anything. I'm just letting it be for t is equal to until t is equal to some 1000 nanoseconds, right? Whatever happens between this 0 and 1000 nanoseconds, also I can model like a channel. Then I make a measurement. Then I make a measurement on this 0 state, whatever that is, right? After 1000 nanoseconds. So whatever happened between 0 and 1000 nanoseconds, from quantum mechanics, we would say that, okay, it should just evolve, the state should evolve. But really, in practical quantum computing, when you prepare the state at t is equal to 0, then it's going to interact with everything around it, right? Between 0 to 1000 nanoseconds, it's not that it is isolated from everything else. It's interacting with whatever is the situation, right? So it can decohere due to interaction with the environment. It can interact with other qubits, or it can interact with the magnetic flux or whatever is around. And so even those interactions also I can model as a quantum channel. So although the inspiration from quantum channel comes from a physical channel like a fiber optic cable, we need not limit that to just the physical channel like a fiber optic cable, but we could consider even the time evolution as a quantum channel, passing a qubit through different gates as a quantum channel, or performing any sort of operation as a quantum channel. I hope that sort of clarifies, what we mean by a quantum channel. Any questions? Yes, Satvik.
Sir, what you just said about we need not restrict it to a physical channel. Sir, I was thinking that even the time evolution would be, in some sense, interaction of the particle with its environment and how it behaves, and it has evolution through its apparatus or whatever that is. So, sir, could you please talk about it more?
I just literally just talked about that right here, right? So if I prepare a qubit at t is equal to 0 and I don't do anything to it, right? Leave it for 1000 nanoseconds, then whatever is happening in between, like this unitary evolution or whatever, that can also be considered as a quantum channel, right? So then we can model that as a quantum channel. So it's basically something that's mapping one state to another state, one density matrix to another density matrix. So anything that maps one density matrix to another density matrix, including unitary evolution or whatever other operation, is a quantum channel. I hope that clarifies your question, Satvik.
Yes, sir.
It's a set of all operations that a state undergoes as it passes from preparation to measurement. So quantum channel can have, Saptagiri can have multiple meanings. It can change from context to context, but ultimately it is something that has an input and an output. The input is a density matrix, the output is a density matrix. So anything that changes a density matrix into density matrix, be it time evolution, be it gates operating on that, be it passing through a fiber optic cable, be it just sitting there for a few seconds, whatever that may be, that maps from one to another is a quantum channel. Any other questions? So remember that anything that can change the density matrix to another density matrix. So even if you literally leave it alone, don't do anything, it's still going to become some other density matrix, like a unitary evolution, right? So then this, because it maps a density matrix to another density matrix, we need certain properties. Like, for example, the first one is a linearity. Any quantum channel, because quantum mechanics itself is linear, right? You have that linearity. So that means that if I have let's say, a convex combination of density matrices. Let's say I have some rho, which is equal to alpha rho 1 plus beta rho 2. Then we require alpha plus beta to be equal to 1. Right? That is the convex combination. These are probabilities. When we add density matrices, we have probabilities and not probability amplitudes. Right? So that's the convex combination. So if I have phi acting on this rho, that is same thing as saying phi acting on alpha rho 1 plus beta rho 2, then I should still get alpha plus beta equal to 1. Right? This should not be changed. Right? Because we have a convex combination. So then we get alpha phi of rho 1 plus beta phi of rho 2. Again, this phi of rho 1 is another density matrix. Let's say rho 1 prime. This phi of rho 2 is another density matrix, rho 2 prime. But alpha plus beta would still remain the same, making the output also a density matrix. Right? So that ensures that probability mixtures are mapped onto density matrix. And it should preserve hermeticity, right? That is, you have all the observables to be physically observable. That is, the eigenvalue should be real, right? So then you have this rho is equal to rho dagger. That is, you take complex conjugate transpose. It is the same thing, like density, whatever are the properties of the density matrix, because phi of rho is also a density matrix, those properties also apply to the quantum channel. Basically, what we are saying is that a quantum channel is essentially giving you another density matrix. And again, positivity preservation, that eigenvalue should be non-negative because they are probabilities, and then the total probability should sum up to 1, right? And so these are some of the most important points for quantum channels. So whatever we talk about, they should have all the properties of just density matrices. So in general, we can represent quantum channels in multiple ways. One of the ways that we use to represent quantum channels is called just give me a minute, please. Sorry about that. I hope you can still see the screen. Can you see it? Is the notepad okay? I guess, yeah. Okay, great. Thank you, guys. So we are going to represent this with something called Krauss representation, right? We're going to discuss what that is. So we're not going to derive it with a mathematically rigorous way because that will take several lectures. But in general, you can express any quantum channel as this. The reason, maybe if you want to understand it just in a very simple way, let's say I have a rho, right? We express rho as psi, right? If I had just state vector representation, right? Let's say I have state vector representation psi. Let's say this is the state at time t is equal to 0. I want to know time at time t is equal to some t1. Then what we do is we apply some unitary operator t is equal to t1 that acts on psi, which would give me, this would give me psi of t at t1. Right? Are you with me? So now if I want to look at rho at t is equal to 0, that would be psi at t is equal to 0, right? And psi at t is equal to 0, right? Now, if I want to look at rho at t is equal to t1, that would be psi at t is equal to t1, and then the bra at t is equal to t1. But this t is equal to t1 is the unitary operator acting on the psi ket. So then we can write this as u, right? Psi t is equal to t0, and the bra for this would be psi at t is equal to t1 would be the bra psi at t is equal to t0 and u dagger, right? So then I can write that as psi t is equal to t0 u dagger. So this psi at t is equal to t0 is simply rho 0, right? So then I would have u dagger, right? So something like that, we are basically expressing a density matrix like several of these operators that act on the density matrix, not just the unitary operator. It could be multiple operators that are acting, right? So you could have A0, A1, A2, like n operators in general, right? So these are complex matrices of equal dimension, and they act on the same Hilbert space, right? So just like how we express any operator, right? So that's what we call as the Krauss representation. And the thing that we require is usually here when we look at U dagger U, for each U dagger, we require U dagger U is UB identity, unitary matrix, right? But here, what we need is basically for all the A daggers, when we combine the entire sum, then that should give you I, right? If it is one operator, that is straightforward. If it is two, you still get I. So because we want to ensure that the trace is preserved, and we have the complete positivity, meaning that our quantum channel, whatever it may be, the trace of the density matrix must remain one if it is a density matrix, right? So each AK represents some sort of a physical process. It could be measurement, it could be time evolution. If it is time evolution, A would be simply be unitary operator. If it is some particular gate, A would be that gate. If it is related to something else, some other measurement or device acting on it, then A would represent that. So in general, we can represent any phi, any quantum channel as a sum of these different operators acting on it, right? So we're going to look at some specific examples so this abstract picture becomes more clear. So the first example we're going to look at is called a dephasing channel, right? So this dephasing channel, right, is making the density matrix diagonal, right? That is, it is getting rid of any terms that are off diagonal, right? So if you begin with some row that has, let's say, P0, P1, C, C star. So when we write a row like this, let's say we are writing this in basis 0 and 1, right? Then we mean P0 is 0, row 0, right? And P1 is 1, row 1, right? And C star belong to the off diagonal elements, which give you the coherences or whatever 1 row 0 or 0 row 1, right? So now a dephasing channel, what if you have phi dephasing channel, then if it acts on row, basically what you end up getting is these terms, the off diagonal terms go to 0. So you just get only P0, P1, 0, 0. So you lose information about C, right? You lose information about C. And so then basically you cannot say anything about the off diagonal elements, right? So it erases the off diagonal elements, and clearly the trace is still preserved because P0 plus P1 is the sum of probabilities, which is 1, right, initially. And finally also P0 plus P1 is 1, right? Are you with me? So if you have some phase information, right, then that phase information is going to be gone, right, with your row, right? Then that you're going to lose that information. That is why it is called dephasing. Because imagine you have some state, let's say you have some state psi, which is equal to 1 over square root 2, right, 0 minus 1, right? Something like that, right? Then your row would be psi, which would be same thing as saying 1 over square root 2, right? 0 minus 1, then here or half, 0 minus 1, right? Are you following me? Okay, I did it. Okay. Okay, very good. So then we can now see that, for example, if I were to take 0 row 1, right? 0 row 1, that is same thing as saying 0 psi 1, right? And what would be our 0 and psi? That would give me half, or 1 over square root 2, right? 0 and psi would give me 1 over square root 2, and psi and 1 would give me minus 1 over square root 2, right? Are you with me? So then our 0 row 1 would be 1 over root 2 times minus 1 over square root 2, right? So that would be half, right? So there is some superposition here, right? So that is going to be lost, right? So then you would, like, this is an off diagonal term, 0 row 1. So it dephases this quantum channel, the dephasing channel. That is, initially you prepared it in some state like this where you had off diagonal elements. You're going to lose that information, and then you get a trace preserving matrix that would just give you the diagonal elements, which would sum up to 1. So you have changed the state, you have added some phase damping or whatever you want to call it, but you lose the off diagonal elements row 0 1 or 1 row 0, right? So we can now represent this kind of thing as two different ones, right? So we can represent this Krauss representation as A0 as 0 0, and A1 as 1 1, right? These are projection operators. So that means what we are doing is we are taking only the projection, so we get rid of the superposition, right? So when you do it that way, you see here that when I represent it in the Krauss representation, I would get A0 row A0 dagger plus A1 row A1 dagger. So A0 would project it only onto 0 states, A1 would project it only onto 1 states, and then here you're adding density matrices. You're not adding superposition of row of psi itself, right? Recall the difference between adding psi versus adding the density matrix. When you add the density matrix, there is no superposition here. For example, if I have psi, right, if I add 0 plus 1, right, that becomes a superposition, right? Here I'm not adding 0 and 1. I'm adding the probability of finding 0 plus probability of finding 1. So in each case, I know certainly, if it is the first case, I know certainly that the outcome is 0, and the other one, the outcome is 1. I'm adding the probabilities of the outcomes. So I get rid of all the phase information that would be stored in some sort of a superposition state, right? So that's why we call this as the dephasing channel. So a simple representation of dephasing channel for a 2-qubit state would be this way. For example, if I have a basis for some n-qubit state, like let's say I have 2 qubits, then I would have 0 0 0 1, right? 1 0 1 1, right? Then I can build a dephasing channel just like this. So I can build, AI would be equal to the ith vector in your basis, and you build that way, so that you project it onto that state and you take only that state. You take the probability of finding it in each of the basis states, which would become basically the elements along the diagonal, and rest of all the elements become 0. So all the off diagonal elements are lost. So you're simply projecting them onto each of the basis states. So that's a simple representation for a dephasing channel, which would get rid of superpositions, right? Are you with me? Are you able to follow? Any coherent terms are lost in our dephasing channel. So recall that we can also represent any 2 by 2 matrix in terms of Pauli matrices. So if I take a 2 by 2 basis, then you can think about A0 being just the identity matrix, right? And A1 being just sigma z, right? So you're projecting it onto sigma z, right? So that gives you, that gets rid of the reason we're picking sigma z and not sigma x, sigma y is recall that, let's say, any 2 by 2 matrix, I can express it in terms of, let's say, A is some 2 by 2 matrix. Then I can express it in terms of a combination of I plus sigma x plus sigma y, right? Plus sigma z, right? This is the general way where I can express any 2 by 2 matrix as a linear combination. Sigma x and sigma y have off-diagonal elements, right? For example, sigma x would be 0, 1, 1, 0. But I do not want any off-diagonal elements. So I get rid of this. Same thing, sigma y has off-diagonal elements. So I get rid of anything that doesn't have off-diagonal elements. So then my the quantum channel to get rid of off-diagonal elements, the coherence terms, would be just consisting of matrices that have only diagonal elements, like the diagonal matrix, identity matrix, and sigma z. Sigma z would be 1 minus 1, 0, 0, right? So then so then that's why we have only I and sigma z, and each of them would give the same 1 over square root 2, 1 over square root 2, such that when I do A0 A dagger, I get half, and I get a convex combination of the matrices, right? And because sigma z is a real matrix with real eigenvalues, right? Then I can write sigma z dagger would simply be equal to sigma z. You can it's a 2 by 2 matrix that you can see right away, right? So sigma z dagger is same as sigma z. So this is the quantum channel that I am representing as delta or dephasing, delta for dephasing. So it takes a state that has off diagonal elements and makes the coherence vanish. So you can consider this as coherence terms are vanishing, or you are getting a classical probability mixture. It is no more a quantum probability mixture. For quantum probability mixture, you add probability amplitudes. If you just add probabilities, it doesn't become a quantum probability. For example, if I say I'm going to toss a coin, I have half the chances for getting heads, half is for getting tails. That's not a quantum state. That's a classical probability mixture because we are adding probabilities, not probability amplitudes. I hope that makes it clear what we are dealing with here. Are there any questions on the dephasing channel? No? Did you understand what the dephasing channel is? Um, okay. I'm assuming that you guys are listening and you are understanding. So, okay, as we discussed, quantum channel is a kind of mapping between two density matrices, or we can say between initial and final. So can I say that discretization of that mapping? Yes, not, I wouldn't say discretization. You can sort of say that, but what we are saying essentially is that multiple things can act, but they don't have to be individually unitary, right? So it has to be overall totally trace preserving. Like for example, here if you come here, right, the trace preserving condition is for all the matrices. So if I have these A's, right, then each A, like let's say I have A0, A1, A2. I don't require each of these to satisfy the condition. A0, A dagger is equal to I, A1 dagger A is equal to I don't need this. If I have the overall, that is A0 dagger A plus A1 dagger A1 plus A2 dagger A2 to be equal to I, that is enough, right? So whereas if you have the other one, the unitary representation, then I require each unitary operator to be having U dagger U equal to I, right? So Yeah, so in that sense, if you are just talking about all the operators to be unitary, then individually unitary, then yes, you can think of that as discretizing. I wouldn't say discretizing, I would talk about it as separating, deconvoluting one process into multiple processes. Like for example, when we say dephasing, we can deconvolute the dephasing process into projection along 0 plus projection along 1. I hope that answers your question, Subhanshu. Any other questions? Okay. So now, for example, now if we use the simulator when we have been working on the codes, but that is a noiseless simulator, no dephasing, nothing. So now you can see right away, I can add something to that simulator, like a dephasing channel with some strength, right? And I can vary that strength of the dephasing channel, but I can add that with some strength and say that I prepare it in some state and I have some dephasing, right? Some coherence terms going away. So now I have modeled some sort of a noisy channel, right? So I hope you are able to see where we are getting that the idea of developing these is twofold, that we can model the realistic channels as well as we can use the those models back in the simulator itself, right? Then next we are going to look at a depolarizing channel, right? A depolarizing channel is basically going to take anything and replace it with a maximally mixed state, right? Maximally mixed state would give you basically the total. If you remember, the trace of rho is always one, and if trace of rho square is also one, we call that as a pure state. And if I have my dimension to be d, that is, let's say if you have a two qubit state, then that is 0 and 1. I mean, 2 qubit meaning qubit with 0 and 1. The dimension, it's a single qubit, but two states. That's what I mean, not two qubits, but 0 and 1. Then the dimension is 2, right? Then trace of rho square, if it is equal to 1 over d, then we call that as a maximally mixed state. Maximally mixed, right? And recall that maximally mixed state, right? Why we called it maximally mixed state is if we go back to look at the entropy that we calculated a little bit earlier in the lecture, right? So if the measurement outcome is not revealed, we have a maximally mixed state. That means the entropy is maximized, right? That's why it's a maximally mixed state, because the entropy is high, right? So you have maximum uncertainty in a mixed state. And so what we are doing with a depolarizing channel is we are taking a state with low entropy and converting it into a state with higher entropy. In fact, maximal entropy for that. So then what we are going to do is, previously we did dephasing. This is depolarizing, meaning I take any state, now I will project it along all different basis states. That is all different combinations, 0, 0, 0, 1, 1, 0, and 1, 1, right? And so that I would get, whatever I would get would give me, a maximally depolarizing state. So like Subhanshu was mentioning earlier, right? That you could get basically get this kind of a deconvolution into different kind of projector operators, right? So you project whatever the density matrix you are given along each of the basis vectors and then put the other basis vector, right? So you get these other terms, off diagonal terms here, right? So you want to make it maximally uncertain. In the previous case, you're sort of making it diagonal. So you're removing the coherence terms. Here you are depolarizing it by adding those. So you have to consider then sigma x and sigma y, because now we want to add the off diagonal terms. In the previous case, we were removing the off diagonal terms, right? So then we consider sigma x and sigma y as well instead of sigma z. And then so we can then express the total thing as sigma x, sigma x rho y, sigma z rho y. So this is also called a poly channel, right? So each one comes with a probability of 1/4. In the previous channel where we were dephasing, we removed the off diagonals. So we removed these two channels. So this probability became half here. But here we are adding, so we get these off diagonal terms. So these are two simple channels that we could use to model what is happening in a quantum channel. That is, given a state, that state is not going to remain like however you prepared it. So I could either dephase it or depolarize it, and I can change the strength of these polarizations. That is, I don't have to distribute this equally, right? I could distribute it whichever way, as long as they add up to one, right? Then that's fine, right? I just want the total to be one. So I could depolarize it more along X or Y, or different ways, right? So in fact, you can consider the dephasing channel as a special case, right, of the previous channel, right? So let's look at some code. I'm going to paste the code in the chat box. So please open the code, and we'll try to work on these channels on simulator and real quantum computer, and try to see, try to get some hands-on on these channels, on how to make these channels. And again, please make a copy, and please confirm that you have changed the API token and CRN so that it runs. And so I hope you're able to see the code. Please confirm once you have opened, copied, and you started executing it. Are you guys able to access it? Okay. I see yes from two people. I hope others are also able to access it. Okay, thank you. So let's see what we're doing here as it is running. So first, again, this first part is standard, right? We are just putting some backend, right? And then we are defining a Bell state to begin with. So we're defining 5+ state, right? So then we have 0, 0, and 1, 1. Is this a maximally entangled state? Please verify for yourself whether it is maximally entangled or not. It's a Bell state, right? So we're starting with 5+, which is 1 over square root 2, 0, 0 plus 0, 1, sorry, 1, 1, right? We're starting with this, right? And so then we are preparing manually what the so row before, you can see that you should get two diagonal elements 0.5 and 0.5, which sum up to be 1, and two off diagonal elements 0.5 and 0.5, right? You can verify that for yourselves, right, to make sure that you're able to make the density matrix, right? And then we're applying a manual dephasing channel, right? So a manual dephasing channel, that is, we want to get rid of the terms that we have along the off diagonals. So we are going to use two operators, right? One is projection along 0, another is projection along 1, right? So that's exactly what we are doing. We're projecting along 0 with lambda, right? And projecting along the other one with 1 minus lambda, and you can change the value of lambda here to different values, right? And then we get whatever the cross representations are, right? That is, we are doing K0 conjugate. So we are applying something like we're building, here I'm calling, instead of whatever we called AK, rho AK dagger, right? I'm calling it as simply K rho K dagger, right? That's exactly what this line is doing here, that after that, it will be whatever is, K0 K dagger, right? And then, so that's how we are defining the dephasing channel in the simulator, right? So this part, we're not doing anything on a quantum computer. I'm not initialized any qubits. I'm just doing math. Okay. I hope, are you guys following me? Any questions? So in the first part, I'm just doing simple math. Then I'm going to actually now prepare a quantum state. So I'm defining the number of shots. Now I'm preparing a quantum circuit with 2 qubits, right? And because we want to make, remember in Qiskit, the convention is the rightmost qubit is the first, is the 0th qubit. So when I prepare a quantum circuit with 2 qubits, this is Q0 and this is Q1. That is the 0th qubit, and that's the first qubit, right? So, and then I'm applying Hadamard gate, right? So when I initialize, both Q1 and Q0 would be 0, 0. That is what my first line is doing. And when I apply a Hadamard gate on 0th gate, what is going to happen? Anyone? What does the Hadamard gate do? So this is same as 0, 0. Yes, that's right. So Hadamard gate, that's right, is going to give us 0, 1, right? So after I apply Hadamard gate on 0th qubit, that is this qubit, I get this output. That is what is happening in the highlighted section. And then I'm going to get, what I get is 1 over square root 2, 0, 0 plus 0, 1, right? That is the same thing as this state. I just expanded it out. Then I'm going to apply a C0 gate, right? Again, C0 gate, I'm applying only on this qubit, right? So I'm applying only on this qubit, right? So then I would just basically get when it is sorry, again I miswrote it. So the way I should have written that is yeah. So we are applying the C0 gate on this part, right? And again, 0th qubit, right? And the first qubit. So if you have the C0 gate on 0 gives you 0, and C0 gate on 0 gives you 1, and 1 gives you 0. So you should get 1 over square root 2. This should become, no, it changes only one thing. It changes 0 to 1 or 1 to 0. 0 and 1. So basically that should give you 0, 0, and it should change this to 1, 1. So that's what you should get. Because C0 gate changes, so C0 for, when I write in the normal convention, qubit 0 is 1, qubit 1 is 0, it changes this to 1, 1 state. That is what the C0 gate does. So here that state will appear like 0, 1 because in Qiskit the qubits are flipped. We usually write it as Q0, Q1, but in qubit it is written the other way around. So the C0 gate flips 0, 1 to 1, 1. And it leaves 0, 0 as such. So that's what the C0 gate is. So so we get then after the C0 gate, we get the maximally entangled state, the Bell state. Now, what we want to apply is we want to measure in all the bases, XX and ZZ bases, right? And so what we're trying to construct is we're trying to construct multiple shots with different density matrices to see what we can get for first qubit and second qubit, right? So we are going to dephase it, but we are not going to completely dephase it. We are going to give it some dephasing strength. And what we are going to do is we're mainly to dephase it. Recall that if you want to completely dephase it, we remove X and Y both, right? So here I'm removing Y, but I'm still measuring X, right? So circuit without Z, and I'm defining these different circuits. And then I'm running it on these different circuits to get for different number of shots, right? And we're getting the dephased probability, right? So here, what you see is the initial matrix has 0.5 and 0.5, right? Ideal density has the off diagonal elements, and ideal density matrix after dephasing would have the zero off diagonal elements, right? So when we do that with whatever strength, then you see that in reality you would get just if I did in ZZ basis. That is, I completely remove the off diagonal elements. That is, I do not consider X or Y. If I consider X or Y, I would get off diagonal elements. So I completely remove X or Y and I do it only in ZZ for both first qubit and the second qubit. Then you see that the off diagonal elements have gone to almost zero, and you get some non-zero value here to the second digit, but you have dephased it, right? You can play around with this. You can play around with just doing XZ or XX, and you can multiply with different probabilities through this, and then you should be able to see how you are able to dephase that, right? And then in the second example, we have a depolarizing matrix that is going to make it maximally mixed. So again, you start with some state, and you measure X, Y, and Z and mix them up. So to do all these runs, what we are doing is we are using this kind of Krauss representation. So we can represent A0, A1, A2, A3 as these operators. So that would be just be measuring sigma X, sigma Y, and sigma Z, and then adding them up. In previous case, for dephasing channel, we were just using just the sigma Z because we wanted to get rid of the off diagonal elements, right? I hope that makes it somewhat clear to you. Any questions? So after you run this, you could check that. So you see that you had 0.5, 0.5, 0.5, 0.5 off diagonal elements, but now you get these only diagonal elements. This is just math, no quantum computer here. The quantum computer part is running. So what you do is you take whatever is the initial state, initial density matrix, and you apply the cross operators like we have. You build those sigma X, sigma Y, sigma Z, and you add those. And because the cross operators have the form of a dagger, right? So you have like a rho, a dagger, right? So you are going to multiply it with sigma X rho, sigma X dagger, which is also sigma X. And if you do sigma X square, you see that you will get diagonal elements, right? So or sigma Y square or sigma Z square, they should all give you diagonal elements. So that's how we get the entire thing to be diagonal. So the way we are putting it into the quantum computer is simply make the measurements along X, Y, and Z, find what is the expectation value along X, Y, and Z, and change it to those states to express it as a linear combination of Pauli matrices, right? That's exactly what we are doing here. So we are defining different bases, X, Y, and Z, right? If it is along X, then you change to this Y basis, right? If it is along Z, you change to Z basis, right? And you apply that Pauli gate along that particular axis, and you make that measurement, and then that's what is going to depolarize it. So here we are using different measurements to model the quantum channel. I hope you're able to see what we are doing here. That if I have a simulator, the simulator is just going to simulate like whatever state and leave it like that. It's not going to evolve, not going to change, and just leave it like that. But if I find that my situation, whatever physical situation I have, has some dephasing or depolarization. For example, like let's say I'm making some photons that I'm going to use to communicate, or I'm making some spins that I'm going to pass some information, then there is going to be some time delay between me making the spin and passing it to something. So when I want to just make a simulation or model this process to understand what is happening, then rather than just creating the state and passing it through the gate, what I would do is create that state, add some dephasing or depolarization, which I would model as again these operators that I just showed you in between. So that gives me more realistic model. So that's how you make noisy simulators. Noisy simulators are made by adding these kind of gates in between, right? So you can model a noisy physical channel using some gates. That is, imagine I have a fiber optic cable through which I'm going to send this, and that fiber optic cable is a dephasing cable. That is, I lose all the probabilities along the off-diagonal terms. Then in a real quantum computer, I could model that fiber optic cable as a dephasing channel, which would retain only the identity matrix or sigma z. So I can apply the gate along sigma z and model the channel that I have, the physical channel. Am I making sense? Are there any questions? It is taking somewhat a long time to run. So we'll wait for some more time to see whether it runs. But I hope you are able to follow with me what we are doing. And I hope all the codes that we have been sending, I hope you are making copies and fiddling around with those and trying them out to understand. There were actually some questions about using the code, which I will address right after showing you the result. So again, so now we depolarized it, so now it gave pretty much almost equal probability along diagonals, right? So you average them, and so we are getting what we expect in terms of depolarizing channel. So some of you have raised a question that you have not written this code, and this code was written by somebody else like me, or you may be using ChatGPT to write the code. Is that okay? So what I would like to say is, if you use any kind of GPT to write the code, that is fine, but you should be able to look at the code and understand what it is doing. For example, like let's say I asked it to generate this, that is, go through this and count and append to a list. I can understand that this is a for loop I'm going through. I have multiple results. So I'm going to result a particular integer. I'm getting the counts from there, and I'm creating a list to which I'm appending, right? Because I want to access these counts later to show the density matrix, or whatever. Like if I applied like this QC dot wherever this was, like prep dot h0 prep dot cx of 0, I'm using this to create a Bell state, right? So as long as I understand that, even if I don't remember the exact criteria, like for example, if you ask me what is the exact command for accessing the probability counts in the result that you get after you run on the quantum computer, I may not be able to tell you. All I can tell you is I can run this job. Was there a question? All I can tell you is I can just run this job and I get this result, but this result of dot data dot c get counts, I may not remember, but I understand what it means. So if you use GPT, that is fine, but you should understand what each line means. And what I recommend is you go through the thing like by yourself through the code and see, like, make x is equal to 0 or 1, and go through the code and see if you're able to go through step by step and understand what it means. And if you do not get what it is, again, you can go here and explain the code, right? And try to make sense of that. So do not blindly use whatever you get and cut, copy, paste and run it, and you did something like that. But GPT gives you the ability to code in natural language. So as long as you're able to understand the algorithm that is behind it, that is more important than knowing the syntax or semantics of the code itself. But if you are not able to understand the algorithm, then that's a problem. How do you understand the algorithm? How do you develop the intuition? There is no instructions to develop the intuition. You either have intuition or you don't. That is what intuition means. That you cannot develop that intuition, right? I cannot give you a process of steps to develop the intuition. That is exactly what is the difference between GPT and a human being. That GPT has no intuition, right? But as human beings, we have intuition, right? That I can intuitively understand math. Whereas you have a computation, meaning a deterministic number of steps in a large language model or something that is giving you these steps. But coming back to you, the questions about can you use GPT to code? Yes, you can. I use it all the time, to be honest, because I mean, I'm one lazy to write the code myself. Even though I know it, I don't want to write it. And second thing, I understand the code, I understand the algorithm, so I'm telling it what to write. I'm giving it the algorithm, so it's sort of programming in natural language. So very soon, or actually even now, I could say that we are programming in natural language pretty much. It is just like, I do not actually know when I write some code, even before pre-GPT, let's say C, C++, if I write, I is equal to I plus 1, I understand what I is equal to I plus 1 is, but I don't know what is actually happening behind in the compiler and how it is actually going to the, whatever transistors and chips in the computer and what is happening. I really don't understand that. I only understand, I can include some header file and add something like that. So that language has come up one more step in terms of natural language, but still, again, you need to understand the algorithm. So as long as you understand the algorithm and you have some natural intuition to understand that, it is fine to use GPT, but don't blindly cut copy paste. And it is always good to declare that you have used GPT, and say acknowledge that I have used GPT, or whatever tool that you have used. You can acknowledge it so that somebody may not find you at fault for using that. Like I said, like I use GPT to like I wrote the algorithms for some of these, and I was getting errors when I was writing it because I was writing it in the old Qiskit form before it was migrated to cloud. And after it was migrated to cloud, some of the commands changed. For example, like how you access this counts from the result, that changed. So the way I was writing it was giving me errors, and I didn't know how to access it this way. So I asked GPT, how do I access it? And it looked up and gave me some answers. And then there I figured out that this is how you access the result, right? So I hope that answers the question. Are there any other questions? No questions? Were you guys able to understand quantum channels? Sort of. Yes, no. It would be okay. I see one yes. Little bit. That's good. Uh, yeah. So again, this course is not meant to go into great detail about every topic because we have only 10 days. But the idea is you have these codes, and now you have these PowerPoints, and you can go through the notes, and then you do your own research on it. So hopefully this gives you the initial momentum that you need, and with that initial impetus, you can propel yourself forward, right? So uh, so please use these codes, try to play around and get some intuitive idea about what these mean. We will stop here, and when we come back, thank you, Mahesh. Thank you, Subhanshu. We'll come back at 4:45, and then I'm pretty confident that the next lecture we are going to do on quantum key distribution, especially the BB84 protocol. I think it's going to be very nice. It's a very simple code. I think you can directly understand it in a much better way than quantum channels, which are a little more abstract. So we'll come back to quantum information and discuss specifically quantum key distribution protocol called BB84 and do a hands-on experiment with that in the next session at 4:45. So please come back at 4:45. I'll see you then. Thank you. Okay. I'm going to end the poll, and then I have a quiz to follow up. Okay. You have a quiz on your screens. Please take a minute to answer.